So here's a typical starting problem with the MVT. Let's verify the MVT, the mean value theorem, for the function f of x equals x squared on the interval -1 to 2. When I say verify, and this is what the problem would mean if it asked you to verify, what it means is that verify that the mean value theorem, verify that the thing that the mean value theorem claims will be true is actually true. So what does the mean value theorem claim? Recall that it says that if f is continuous on the closed interval ab and differentiable on the open interval ab, then there should be at least one number c. I'll put it in here. We don't know exactly where it is, but we can guess a little bit. There should be at least one number c such that a particular equation is true, which means that the tangent line at that point should be parallel to draw it a little better, should be parallel to the secant line passing through the endpoints of the curve on that interval. So we'll certainly verify that f of x equals x squared is continuous on -1, 2 and differentiable, I'll just write diff, on -1, 2, on the open interval -1, 2. We don't really need to do anything further to verify that. We all know that the derivative of x squared is 2x, which certainly exists on that interval, and clearly x squared is continuous on the closed interval -1 to 2. So what we want to do is verify that there is a c in -1, 2 such that f prime of c is equal to f of 2 minus f of -1 over 2 minus -1. That's what the mean value theorem asserts, so let's verify that it's true. I've put in the actual endpoints here, so we can see that 4 minus 1 is 3 and 2 minus -1 is also 3. So the slope of the secant line is going to be, f of 2 minus f of -1, so that's 4 minus 1 over 2 minus -1, that's going to be 3 over 3, which is equal to 1. Now, we see that the derivative of x squared is, of course, 2x. So, let's see, is there a point, if I solve 2x equals 1, I get x equals 1/2. So the assertion is that if I set c equal to 1/2, then the derivative is going to be equal to the slope of this secant line. And because of the way we even found x here at 1/2, and that's because of the way we found 1/2, we know that in fact the slope of this tangent line is 1, and of course we already calculated that the slope of the line connecting the 2 points is also 1. So this is in fact true. We can see that the number does exist, and we can also assert that 1/2 is in the interval -1, 2, which is what the mean value theorem asserts. It says not only that there will be such a point, but that it will be in this specific interval. So we've done the work now. We've verified that the MVT does in fact work for this function on this interval. I realize that a lot of you are sort of confused because you're like, I like to solve a math problem that involves calculate this. And unfortunately, as we get further and further into calculus, problems don't really work that way. There are a couple of problems in the book that say verify that the MVT applies to some function on some interval, and this is really what they're asking you to do, is to verify that the function is in fact continuous and differentiable on the given interval, and then that the number c that's asserted to exist actually does exist.